Hey everybody, thanks for tuning into my lesson on acids and bases. Today we're going to review some of the definitions of acids and bases, and I'll use some reactions as examples, and then afterwards you can take the quiz to review everything. So as you can see, I already wrote up there that under the Arrhenius definition, and Arrhenius was a scientist who came up with these two definitions of acids and bases. An acid increases the concentration of H plus ions in an aqueous solution, whereas a base will increase the concentration of OH ions in an aqueous solution. And to refresh your memory, an aqueous solution just means that it is dissolved in water. Bronsted and Lowry, a team of scientists, determined that the definition of an acid would be that it donates an H plus ion, and a base would accept an H plus ion. So we do see a little bit of overlap between these definitions, but the main reason why Bronsted and Lowry wanted to come up with this definition is that this applies to a broader scope of reactions that may not necessarily happen in an aqueous solution. A strong acid or base will ionize completely in an aqueous solution. You'll see I abbreviated that with AQSOL. And a weak acid or base will ionize partially in an aqueous solution. These two definitions are good to keep in mind because strong acids and bases do act differently in aqueous solutions. The main reason that you'll see is that strong acids will ionize completely, weak acids ionize partially. So I'll go over a few different reaction examples. The first one is going to be an acidic reaction with HCl. HCl is hydrochloric acid. It's going to be in an aqueous solution, and we will put water right there. Right there is the AQ for aqueous. Water is a liquid, so we put L for that. We're going to put the reaction pointing to the left, which means it favors the products. The products are going to be H plus aqueous and Cl minus aqueous. You'll see that H2O dissolves the HCl into these two ions, and the H2O is just kind of hanging out there as well. Then we're going to take a look at a basic reaction with sodium hydroxide. Sodium hydroxide is also going to be in an aqueous solution, so we'll put water right here. It favors the products, and water will dissolve the sodium hydroxide into sodium ion and the hydroxide ion. And water is just going to hang out there as well. The last reaction I want to take a look at is ammonia. Ammonia is NH3. It's also going to be in an aqueous solution, and water is going to be there as well. It will react towards the products, but NH3 is actually a weak base. And because of that, we're also going to put an arrow pointing towards the reactants. This signifies that it doesn't totally favor the products, it doesn't totally favor the reactants, it's somewhere in the middle. This is going to be your big signifier in a reaction if it's a strong acid or a weak acid. The H from H2O is going to jump on to the NH3 to form NH4 plus aqueous, and the H2O is actually going to turn into OH negative aqueous. So as we can see right here, in the HCl reaction, the product has H plus ions, which means it would fall into the Arrhenius definition of increasing the concentration of H plus ions. We can also say that it follows the Bronsted-Lowry definition because the HCl did donate an H plus ion. The NaOH, sodium hydroxide, you'll see on the product side there is OH negative, so it did increase the concentration of OH ions, but it really didn't accept an H plus ion. So we'll say for this reaction here, NaOH is an Arrhenius base, but not a Bronsted-Lowry base. For NH3, we can see that it did accept an H plus ion to become NH4 plus, and it also has OH negative on the product side, so it did increase the concentration of OH negative ions. Therefore, NH3 is both an Arrhenius base and a Bronsted-Lowry base.